In this video, we're going to look at first a function from z to z, and then we're going to cover the freshman's dream function. So we'll get that second. So our function alpha is going to take in an integer. Let's not use a. I'm going to use x just because the function I've named is alpha. And it's going to be the multiply by something function. So what can we multiply by? I don't know. Let's see. Let's multiply by 2024 because it's 2024. So alpha is the multiply by 2024 function. Whatever you give me, I multiply it by 2024. Great. Let's see if alpha is a homomorphism. So let's do the preserves the preserves addition check first. Now multiplication is a linear thing. We saw this happening in the previous video with negation. Negation is just multiplying by -1. Multiplying by -1 is a linear thing. That is, it behaves nicely with addition. So we should expect, without doing any work, that this preserves addition. But let's do the work. So we need to check that if we plug in x plus y into it, that's the same as plugging in x, plugging in y, and then adding them together. Oops, we're not golden yet. All right, so alpha is the I multiply you by 2024 function. So we multiply x plus y by 2024, and then what do we do to x? We multiply it by 2024. What do we do to y? We multiply it by 2024. So is it true that these are equal? Well, yeah, of course. It's the distributive property. The distributive property holds in Z. So does it preserve addition? Yes. Now let's check if it preserves multiplication. All right, so is it true that alpha of x times y is alpha of x times alpha of y? Well, alpha is the multiply u by 2024 function. So if we plug in xy into it, it multiplies it by 2024. If we plug in x into it, it multiplies it by 2024. And if we plug in y into it, it multiplies it by 2024. So we get 2020. So again, we're not sure yet. I mean, we're pretty sure at this point, but this is 2024 xy is 2024 squared xy. Now for us to be a homomorphism, this needs to hold for all x and y. This does not hold for all x and y, though. In particular, it doesn't hold for x and y as 1. So does this work? No. It does not preserve multiplication. Okay, great. And at this point, we know it's not a homomorphism. So technically, we can stop here. However, there is merit in understanding how things fail. And so it might be that it preserves 1, and maybe we learned something there. It doesn't, but it might be. We don't know that. So we need to check. So again, at this point, we know not a homomorphism, but we're going to go through all the checks. So we want to know, is alpha of 1 equal to 1? Well, what does alpha do? It's the multiply you by 2024 function. So is 2024 times 1 equal to 1? And the answer is certainly not. So this is an example of a function that preserves multiplication, or preserves addition, but doesn't preserve the remaining two. So we can conclude from this that alpha is not a homomorphism. Well, not a ring homomorphism. And then we move on. So there's that. Great. Let's now revisit something we did in class. Namely, we're going to talk about a function which I'm going to denote as fr, and it's going to be a function from the polynomials with f2 coefficients to polynomials with f2 coefficients. And what we're going to do is we are going to take in a polynomial, and then we're going to square it. Now, squaring is usually not linear. Usually not. However, here it is, and we're going to see that. So let's go through the checks. This fr, the reason why we have the notation fr, this function is usually called this is called the Frobenius. So that's what the name is of this function. And there's lots of different types of Frobenius functions. This is the one for this ring. All right, let's check if it preserves plus. So we need to check that fr of, I'm going to drop the of x notation. Well, actually, before we even check if it preserves plus, let's just do an example real quick, because this is sort of a weird function. Let's do an example of computing an output to see sort of what it does. Let's look at like x cubed plus x plus 1. Let's just look at that. Sometimes it's helpful to figure out how a function works or to settle into the problem before you actually go and prove things. And so if you're having some trouble like trying to reason with a function that's defined or something you're trying to define, it's often helpful just to sit there with it and plug in some stuff. So what we're supposed to do is we're supposed to square this. And so how do you square this? Well, you multiply it with itself. And oops, I wrote the same thing twice. Now if this was a binomial expression, if I had been thinking when I wrote down the example we're going to plug in, this would be easy. But it's a trinomial expression, and I don't know my multinomial coefficients very well. So we're going to sit here and we're going to just multiply it out, right? Algebra is the manipulation of symbols, so that's what we do. X cubed times x cubed is x to the 6th. X cubed times x is x to the 4th. X cubed times 1 is x cubed. X times x cubed is x to the 4th. X times x is x squared. X times 1 is x. And then lastly, we multiply our 1 through. X cubed times, or 1 times x cubed is x cubed. 1 times x is x. 1 times 1 is 1. All right, so we get x to the 6th plus 2x to the 4th plus 2x cubed plus x squared plus 2x plus 1. And we are in F2. In F2, 2 is 0. So what do we get here? We get x to the 6th plus x squared plus 1. Now, that's a little bit weird, right? It's very odd. In particular, let me just write down what this is, what we computed. We computed x cubed plus x plus 1 squared. And what ended up happening is, so these were equal. We saw that. And this is the result of our just sitting there and doing the algebra. A lot of math is just you sit there and you just write it out and you see what happens. What happens here is really we didn't even look at the cross terms. We just squared each of the individual guys, right? That's exactly what happened to get there. And this is sometimes called the freshman's dream. It doesn't really matter what it's called. The point is that we see some linear behavior, namely, normally when you multiply polynomials, you have cross terms that prevent it from being linear, that is, preserving addition. But here we don't, because 2 is 0. All of our cross terms went away. All right, so we learned something by working out this very specific example. And if this doesn't quite make sense yet, work out some more. Math is learned through the pencil. You have to sit there and you have to write it out to learn. Okay, so let's now check that it is, well, let's see if we can check it's a homomorphism. So now let's do our checks. Let's look at preserves addition. So what we need to check is that Frobenius of P plus Q is Frobenius of P plus Frobenius of Q. And if you don't like the name Frobenius, that's okay. You can call it whatever you want. So what is the Frobenius function on this ring? It says, hey, whatever you plug in, I'm going to square it. So we plugged in a P plus Q, we're going to square it. And on the right-hand side, we plug in a P, we're going to square it. We plug in a Q, we're going to square it. All right, P plus Q squared is P squared plus 2PQ plus Q squared. But 2 is 0. So that term goes away, and what we get is P squared plus Q squared on the left, and that's certainly equal to P squared plus Q squared on the right. Fantastic. So it preserves addition, which is very odd, but nevertheless it does. Let's check preserves multiplication. Now I'm trying to give you some intuition for when these should be true so that you can make an educated guess when you encounter them and then check your educated guess. So our function, the Frobenius function, is defined with multiplication. If it's defined with multiplication, chances of it preserving multiplication are quite high. So let's go in and check that. So what's the Frobenius of PQ? We have to compare that to the Frobenius of P times the Frobenius of Q. The Frobenius of anything is you square it, so we're going to square PQ. The Frobenius of P is P squared, of Q is Q squared. Great. Now, we have a commutative ring, right? So it doesn't matter the order in which we multiply, so this is P squared, Q squared. And are these equal? Yeah, they're equal. Sweet. So does it preserve times? Yeah, it preserves times. Cool. Now let's check that it preserves unity. We actually already saw this with our example, but we're going to do it again. So we need to check the Frobenius of the constant polynomial, which is 1, is equal to 1. The Frobenius is the I will square you function. So is 1 squared equal to 1? Yeah, it is. Awesome. All right. So what can we learn from this? We learn that the Frobenius is a homomorphism because it preserves the addition, it preserves the multiplication, and it preserves the unity. Fantastic. Now the question is, well, what kind of homomorphism is it? Is it just a homomorphism or does it have extra properties? So let's check some of these things. So I claim that here Frobenius is a monomorphism. Namely, this is 1-to-1. And this check, we're going to be able to do better later on in the section. But what we're going to do here is sort of a prelude to the proof of a fact that we can make this easier with later. So this is going to look hard now, but we'll simplify this later. Okay, so how do you check something as a homomorphism? Well, you suppose that P and Q are such that the Frobenius of P equals the Frobenius of Q. And then from this, you try to deduce that the only way for two guys to have the same output is if they were actually the same to begin with. And let's do exactly that. So we're going to suppose this guy here, and we're going to show that P must have been Q. All right, the Frobenius of P equals the Frobenius of Q is what we're supposing. And we can actually subtract over the Frobenius of P minus the Frobenius of Q, and that should be 0 if we subtract over the Frobenius of Q. But the homomorphisms, they behave nicely with respect to the structure. Again, we're going to do this all later, better, but as a taste, we know they preserve addition, they break up under addition, in particular they come together under addition, and we're going to show later that they actually behave nicely with respect to subtraction. And so what we're asking here is, when is it the case that the Frobenius of something is 0? Well, what does the Frobenius do? Let's go back up to it real quick. The Frobenius takes whatever polynomial you plug in, and all it does is it takes the corresponding monomial terms and it raises it to the second power. It multiplies those powers by 2. So how could you get 0? The only possible way you can get 0, right, this increases your degree each time. So the only possible way you can get 0 is if what you plug in is 0. So when we say the Frobenius, sorry, this video is going a little bit long. When we say the Frobenius of P minus Q is 0, what this is telling us is P minus Q is 0, or equivalently P is equal to Q, which is what we wanted to show. So again, we're going to have a better way of checking this later, which is in the same spirit, but for now, this is fine. So we've deduced that if two outputs were the same, the inputs must have been the same. So this tells us that the Frobenius is 1-to-1. In particular, it is a monomorphism because 1-to-1 plus homomorphism is a monomorphism, or monomorphic, however you say it, monomorphism. All right, great. Oops, I was supposed to be in orange. All right, let's go through the last types of orphisms. The Frobenius is not an epimorphism. Because the things that the Frobenius outputs are square. What do you do is you take your polynomial and then you square the monomial. I claim that to see this, I claim that the Frobenius of P equals X has no solution. That is, there is no polynomial such that when you square all of the monomials involved, you get X. In fact, the Frobenius of P only consists of monomials with even powers, as we saw, and we could prove if we wanted to. In fact, maybe I'll have you prove that. But in this example, when we plugged in anything, these were odd powers, what did we do? We squared the powers and made them even. So we will only ever output stuff with even powers. So can it be an epimorphism? Can it be onto? No, because you're never going to find something that gets sent to X. So this tells us this is not onto. So not an epimorphism. And later we'll describe exactly sort of the range of this guy. Okay, so it's not an epimorphism. It fails to be both an epimorphism and a monomorphism because it fails one of them. So therefore it's not an isomorphism. So it's not an automorphism because an automorphism is a mapping from, it's an isomorphism from a ring to itself. Okay, so it's not either of those. However, it is a mapping from a ring to itself, right? The Frobenius goes from polynomials over F2 to polynomials over F2. So we actually have a special name in that case. The Frobenius is an example of, and this is the last orphism, I promise you. Did I just lie? I'm pretty sure I didn't just lie. Yeah. Is an example of an endomorphism. So all automorphisms are endomorphisms. That is just homomorphism from a ring to itself. But not all endomorphisms are automorphisms. Okay, so this was kind of a very involved example, but it's a very important example